In this video, we're going to look at one of the practicals mentioned on the OCR Advanced Information for both higher and foundation, and that is energy transfer to water. I strongly suspect it's going to link to heat capacity, so you might want to watch my previous video on that. But let's look at some typical exam questions for how they might test this. So pause the video now and try these questions. Okay, so part I, is there a random error in this experiment? So let's look at the experiment. So we've got a heater, an immersion heater. That just means you immerse it in water to heat up the water, and then we're measuring the rise in temperature with a thermometer. And then we have our results here. So if we have a random error, we would expect our results, imagine this is a bullseye, we'd expect our results to be all over the place because it's random. Now, are these random? Well, not really, no. They're basically all on the line of best fit. So I would say no is the most likely answer, because almost all of the points, or just the points, are very close to the line of best fit. If we were showing a random error on here, we would expect them to be quite far away from the line of best fit. So these red points would represent our random error. The scientist thinks point B labelled on the graph is an anomaly. Is she correct? Explain your answer. I mean, again, no. Point B is still very close to the line of best fit. Now, is there a hard and fast rule for this? Not really. I mean, if there was a point here, I would say that probably is an anomaly. If there was a point that was here, is that one an anomaly? It's really hard to tell. But this one, I think, is so close. I mean, part of that is even touching the line of best fit. Part B, slightly harder question now. Calculate the gradient or the slope of the graph. So how steep is the graph? So the gradient is the rise over the run, or you might say the change in y over the change in x. So on this graph here, it represents our change in temperature over our change in time. So our change in temperature, we're going to draw a nice big triangle on our graph using a ruler, and we can see it is, what's that, 9.6 divided by 300. 9.6 divided by 300 gives us 0.032 degrees per second. That means every second we are going up by 0.032 degrees. Okay, some more questions. Pause the video and try these final questions. So we've got a 4-mark calculation question, which suggests there's probably more than one step. Now, they have given you both of the equations. Remember, this year, even if they don't give the equations, you look on the formula sheet because the equations are all there. So you just decide what information you need and you look for the equation that has those in. So what do we need to do? We need to calculate the heat capacity of water. So we're trying to work out the heat capacity. Do we have the mass? Yes, we do. Do we have the change in temperature? Well, it says use the results and the gradient you calculated in part I. So what is our change in temperature? It is 0.032 degrees Celsius per second. So I'm going to write that down here, 0.032 degrees Celsius per second. So in 1 second, what does that mean? It means the change in temperature is 0.032 degrees Celsius. That's going to be really, really important. And do we know the change in thermal energy? No, we don't, but we can work that out using this equation here. Do we have the power? Yes. Do we have the time? Well, you might say we don't, but what happens if we just pick a time of 1 second? That means in 1 second, the energy transferred will be 12.8 joules, because this means 12.8 joules per second. So the energy transfer is 12.8 times by 1, which is 12.8 seconds. And then our second equation, 12.8 equals our mass, 0.1, times our heat capacity that we're trying to work out, times by the change in temperature, which is 0.32 degrees Celsius. So that's in 1 second. So now we can say 12.8, 0.1 times by 0.32 is 0.0032 times by our heat capacity. And we now can do 12.8 divided by 0.0032. And that gives us 4,000 joules per kilogram per degree Celsius. And if you remember what water is 4,200. That's pretty close. We can probably be relatively confident that is the correct answer. Okay, part 2. Which of the following is the definition for heat capacity? Well, it is the energy needed to transfer, to change 1 kilogram of water by 1 degree Celsius. So increase temperature 1 gram, no, can't be grams, not 10 degrees Celsius, so B is the only one that's correct here. Okay, finally the 6th marker. So we need to do 3 things. We've got to write about the measurements, we've got to calculate the missing value, and explain what the results show. So in questions like this, I'm going to tick everything off when I've done it. So firstly, calculate the missing value in the table. Well, it's energy mass times heat capacity times the change in temperature. Same equation from here. So put in our numbers, we know what the mass is, temperature, heat capacity, and we got our value here, 16,800. So I'm going to tick that one off. The measurements, what do I need? Well, I need to measure the mass of the water and the temperature increase. So the temperature increase, I'm going to use a thermometer, but it's increase in temperature. So I'm going to measure the initial or the start temperature and the final temperature, and then the change is the final temperature minus the starting temperature. So done that one. Mass of water, well, that's really easy. Use a mass balance to measure the mass of water. But if I just put all of this on a mass balance, then that's not going to be quite correct, because I'm also going to measure the mass of the cup as well. So I'm going to subtract the mass of the empty cup from my measurement of my cup and water. So I've done that one. So I've done the measurements. Finally, what does the result show? Well, as we increase the temperature here, the energy also increases. So the results show that the greater the energy transfer, the greater the temperature change. But they also show us, if we're clever, if we double the temperature, the energy also doubles as well. Doubling the energy causes double the temperature change. There is a name for this kind of relationship, which we could put in, which is that temperature change and energy are directly proportional.